All right, so welcome for our second talk today. So by Yuan Zhou, and he will talk us about Jacobian determinants. So please.
Yeah, thank you for introducing, and also thank you, Zhiqiang, for inviting me to give a talk here. Yeah, I really get honored. The Sorry, I missed the first talk because this morning I teaching complex analysis, so I just finished my class. Yeah, and my talk is about the Jacobi determinant for nonlinear gradient of planar infinity-harmonic functions and applications. I just closed my video. Yeah, I moved this. No. Yeah. I plan to start with p-harmonic function and then infinity-harmonic functions, and introducing the regularity since we already know it, and also some new result, and then go to the regularity of infinity-harmonic functions and kind of newer property. And I will give some new proof for solving this neural theorem, and also discussing the limit problem for p-harmonic functions. I just try to close this. Yeah, okay. The p-harmonic function and is kind of a solution to the p Laplacian equation, and we're considering the Rn, Euclidean space Rn with n bigger or equal to 2, and for this p strictly bigger than 1, then that's infinity. The p Laplacian is given as the divergence of the length of du with power p minus 2, then du. And you can write this in this form. You put this divergence inside, and then calculation you will get. This is given by du is the length with power p minus 2, then this is Laplacian, and then you get this weird term. Once you put the divergence, the derivative in here, you will get this term. And this term, we call it, this is the partial derivative in xj direction, and the partial derivative of u in xk direction, and then the mixed partial derivative second order, and then with this du is power p minus 4. This is standard p Laplacian. And if we move this term, du is p minus 2 to this left-hand side, and we'll get the normalized p Laplacian. It's just the du is power 2 minus p, and with times p Laplacian. The point to write, consider this normalized p Laplacian is that the p Laplacian is p order p homogeneous, but the p Laplacian is homogeneous with order 1. And then somehow it's just the Laplacian and this weird term, the linear combination. Yeah. If we write this Laplace, if p equal to 2, this is just Laplacian. And for p for this p equal to infinity, we write infinity Laplacian as this weird term. This term, we write it with infinity Laplacian. And then the normalized, if infinity Laplacian, we just write as this times dv with, here it should be du is minus 2 power. Then we will see the p Laplacian we're writing as du is power p minus 2 times Laplacian u plus the p minus 2 times infinity Laplacian u over du is power 2. Or the normalized p Laplacian is just Laplacian, and the normalized p Laplacian, the combination of them. This is very convenient to see the relation. Somehow this normalized p Laplacian is the interpolation or linear combination of Laplacian and infinity Laplacian. And the infinity Laplacian you can view as a limit of normalized p Laplacian. This is the from the definition of this operator, you can see this. And then p-harmonic function somehow is the weak solution for this p-Laplace equation. P-Laplace u equal to 0. But here the solution, you consider weak solution or viscosity solution to this equation or viscosity solution to the normalized p-Laplace, they're the same. This is proved by Gentile and English method in 2001, and then the later one is given by Pearson and Sheffield in 2009. And in this talk, I will denote UP as a p-harmonic functions. And for p bigger than 1.2, this equation is called the linear singular elliptic equation. When p bigger than 2, it is called linear but degenerate elliptic equation. I mean, this singular or this degenerate is caused by this term. It's caused by this term. Also, we know that p-Laplace equation is the Euler Lagrange for this minimizer for LP-LH. D with power p minus, here should be p, not p minus 2, the integral over domain. And there is a very rich theory for the existence and the uniqueness. We don't go to that. And its relation with this kind of, in dimension 2, there is some relation with this Bertrand equation. If we consider this complex gradient v z equal to this 1 over 2 times vx, the derivative of v in x direction minus I times v y, and this v z bar, this partial derivative, we write this. This is as a conjugate of this guy. And then we define this f as this partial derivative of uz for p-harmonic function u. Then we will see it satisfies this complex equation fz bar equal to mu times fz. And moreover, if we write g equal to f with power square root p minus 1 minus 1 f, then this g satisfies also the Bertrand equation like this. There's some kind of collection. And then we try to understand the limiting problem for these p-harmonic functions as p goes to infinity. Give a bounded domain omega and some fixed boundary g in Dp's class. Of course, we require this domain is somehow like ball or smooth. And for p bigger than 1 infinity, we did it by up the unique p-harmonic functions with differential boundary g. And then what can we say about the possible limit behavior of up as p goes to infinity? What it is? We let p go to infinity, what's the limit of up? This we want to understand. And from the operator relation, it somehow should be those infinity-harmonic functions. And we remember, we recall that a function is called infinity-harmonic function if it is a viscous solution to this infinity-Laplace equation. And also it is the viscous solution to the normalized infinity-Laplace equation. And we know that the rank, this equation, the coefficient of this second order derivative is this. And this guy is a tensor of the gradient of u. It has rank 1. So this equation is highly degenerate and nonlinear. But there's some example for this infinity-harmonic functions. The linear function or a coin function outside of the vertex. And also several solution to this Euler equation. And also Aronson's infinity-harmonic function, like x1 with power 4 over 3 minus x2 with power 4 over 3. I mean, this is founded by Aronson. This is an infinity-harmonic function in the whole Rn. And this kind of infinity Laplacian is comes from minimizing problem for an infinity edge. This is introduced by Arthur in 1960. He tried to find some kind of absolute minimizer. Because minimizer for this guy, there are many. You give a boundary, then you make string extension, you get many of this kind of minimizer. But then, but the minimizer is not necessarily locally minimizer. They also introduced this called absolute minimizer. It is minimizer each subdomain. That's for every function. If U is a absolute minimizer, if for any subdomain, any V with some boundary on this in this domain V, then the edge of U is also is always smaller than the edge of V. Also, this shows that this infinite Laplacian is the Euler Lagrange for this absolute minimizer. And important work in this direction is given by Jason in 1993. He shows that the infinity-harmonic functions are exactly the absolute minimizer, and also proved this existence and the uniqueness theory. Then we have this the limit problem have some solution. In our domain omega and the given boundary with C01 boundary, Lipschitz boundary, we denote by U infinity as the infinity Laplace harmonic functions. Then we will see as p goes to infinity, we have these p-harmonic functions will go to infinity harmonic functions in C0 alpha for any alpha less than 1. And also weakening W1Q for any Q less than infinity. This is somehow this is known by together with Jesse's work. This is known by kind of Manfredi's work in 1989. And then I mean we try to find other better convergence property for this. And then for this, we need some regularity for the p-harmonic functions and infinity harmonic functions. And so we recall some regularity for p-harmonic functions and call the regular property. In dimension 2, we know that p-harmonic functions have some sharp regularity. This is given by Yuan Zhou and Manfredi in 1989. Also obtained this. They proved that this p-harmonic functions always in the class ck alpha, also wk plus 2 q. Q is less than this. And this k plus alpha is given by this. But this is this kind of weird relation, but it is sharp. They proved this by this kind of holograph method. Recall list the approach a little bit. Recall that the complex gradient is given by UZ. And we assume the gradient of U at 0 is 0. I mean, if this UZ is not 0, then the function U is always smooth in this neighborhood. So the problem comes from the critical set. So and the critical set of the p-harmonic functions is always discrete. This is proved by Boyakovsky and Ivanich in 1984, I think. So we can assume this 0 is the derivative, 0 is the critical point, and with this UZ at 0 is just 0. And then we can decompose this f at this point. I mean, at this point, we can write f as the the n power of some quasi-conform mapping.
So sorry, what is F here?
What?
What is F? I mean, you.
No, no, no. F just using.
Oh, I see. Okay.
Sorry. Yeah, I should address using. Using is kind of quasi-regular. Quasi-regular mapping can be decomposed as the kind of the with power n of some quasi-conform mapping. This is
Yeah.
sorry. Here is using, not there. This is somehow lower that, and then using this, they denote by h as the inverse of chi. This quasi-conform mapping is still a quasi-conform mapping. And then calculate this chi with this derivative of z in z and with the derivative in z bar. They get this. And this J is just Jacobian of h. And then they show that this h solves this system. H is equal to this is given by 1 over 2 minus p 1 over p, then this term. And in the unit disk, the physics use this kind of approach to show that the solution for this equation must be this, like this. Must be like must like this. And then they show here this kind of complicated things. But the point is that at this critical point, and the solution must given this form. Once you have this form, you can compute the sharp regularity. That's the point. The sharp regularity somehow comes from the n and also this index. And you can see this for more details. You can see their paper. And then if we write this nonlinear complex gradient v beta du as uz with power beta and uz, and by Bohowski and Ioannich and also Manfredi. Sorry, here should be this v beta. This is a regular mapping, and the v beta is in W12, and this kind of derivative is controlled by this Jacobi with this coefficient, with this constant. And this constant is given by this, and this is sharp. The sharpness you can, I mean, in this paper, they didn't give this exactly clearly this, but using their if you go through their approach, you will find this constant, and you will see this is sharp. And here, in particular, we will say that this kind of Jacobi is in L1 because this in W12, this in L1. And even more, we know that this is in L1 epsilon, L1 plus epsilon. And in case p bigger than 2, if we write this f as this kind of complex gradient of u, then Bohowski and Ioannich in 1984 also shows that f satisfies this complex equation. And we can write this equation. We can write this as a Bertrand equation. Fz bar equal to mu Fz, and this is mu. And you can see this regular coefficient is given by this. This is this regular set of this p-harmonic functions. And in the literature, there's many results from this from the real, not from the complex point, but from this kind of real analysis from PDE side. And using C1 alpha, this is started by Uzaraba and Lewis and Evans and Uhlenbeck. And also
Sorry,
this,
quick question, but these are now results in all dimensions? I mean, the previous results were just in dimension 2, right?
that's only dimension 2, yes. Here only dimension 2.
No, but I mean, the result that you mentioned on the next slide, is this also only in dimension 2, or is this in general?
You mean this? This
Yeah.
is all dimension. All dimension.
Oh, I didn't see that. Okay, thanks.
Yeah, this is in all dimension. Yeah. But this is the use PD approach. Yeah. And also this complex derivative du is power 2 over p minus 2. This is W12. when they prove this, they also get this. And also, when p bigger than 1 than 3 plus n over minus 2, then Maffei and Weizmann shows U in W2Q for some Q larger than 2. And if n equal to 2, that's just infinity. But when n bigger to 2, this is limited range. But for p bigger than this range, we don't know what the regularity should be. And recently we can show that this du is power over p minus gamma over 2 du in W1Q. And this gamma have a range like this, weird range like this. This is when equal to this goes back to Biohazard and Yuanic. When p equal to 2, this just p minus p plus 1, then goes back to the Biohazard and Yuanic and Maffei. When n bigger or equal to 3, this is obtained by us and by Hongye Dong and my student Peng Fa and Yi Zhang and me. And also Sasa improved our result for p less than 2. And even more, we can get some kind of generation of quasiregular property to higher dimension. I mean, in dimension 2, the quasiregular property size, the Hessian is with the Hessian, the length square of Hessian is controlled by the Jacobian. But in higher dimension, what we can get is the sigma 2 controlled as Hessian with square 2. Here, sigma 2 is just this guy. You count this every two-dimensional matrix for this matrix M, then summation of the determinant of each two times two submatrix. Then take summation, you get sigma 2. And then this is controlled this. If n equal to 2, this goes back to the quasiregular. But if n larger or equal to 3, this is something new. I think this is something new phenomenon. But I don't know if there is some. One question comes to my mind, but I didn't get any answer. Is there some kind of property under this control in higher dimension? Is there some topological or geometry relation? But I have no idea.
So, what is actually the relevance of this sigma 2? I mean, can you?
Sigma 2 is just this. Yeah.
I mean, I understand. I mean, this is just a definition, but to understand this on a more conceptual level, can you somehow express this in terms, for example, of the eigenvalues or something like this?
Yeah. I mean, in terms of eigenvalue, this is me. Quasi-conformal or quasi-regular means this largest eigenvalue is controlled by this kind of smallest eigenvalue. Yeah. The largest one controlled by a smaller one. But here, this means this the eigenvalue of here is controlled by this. Here we get the largest eigenvalue is controlled somehow by the or square. Yeah, this. Let me see. Yeah, is controlled by this combination of lambda I, lambda j. This term. Maybe I can write something.
Can you write something? I don't know.
Try to find a pencil.
Oh yeah, sure. Yeah.
Here means that it's right here. Write the largest one. Somehow controlled by in dimension 3.
Yeah, I see. Oh, I see. So it's the sigma 2 is just a symmetric combination of
the. It's controlled by this guy. The combination of this guy. Yeah, this is sigma 2. I mean, if this is dimension to this goes back to quasiregular, but in higher dimension, I think this is at least from to my knowledge, this is the first thing I see.
Well, in Riemannian geometry, they often look at these kind of symmetric functions of eigenvalues in some
Yeah,
context.
yeah, this kind of relate to this kind of scalar curvature or something.
Yeah, I see. Okay, yeah.
Yeah, yeah. But we didn't. I mean, I tried to understand something here more, but I didn't get any idea. Yeah, I tried to erase this. No. And then the regularity of infinite Hamming function and is kind of a big problem in this field. I mean, by guessing this, the infinite Hamming functions are always absolute minimizer and also the and and hence local nippies. And by Radon theorem, this infinite Hamming functions are always differentiable almost everywhere. But Ariston's example shows that this function Sharp regularity of this function is C1 1/3 and W2 Q less than 3/2. And then from this ellipse to this regularity, there's a big jump. And the main conjecture in this field is infinite Hamming functions are C1 1/3 and also W2 Q less than this. But this is there's some progress for this conjecture, but low for result. And for this neural theorem, Aronson shows that if UN C2 is a global infinite Hamming function, then it must be linear function plus some constant. And by Evans, for C4 solution, also have a similar result in higher dimension. And the Crandall and Evans and Garp in 2001 shows that if you have some lower bound, it must be constant. Or if U is growth is less than linear function, it must be constant. And the conjecture by Crandall and Evans Garp ask if an infinity Hamming function, if it is linear growth at infinity, then it must be linear function plus some constant.
A quick question about this. Is this actually true for p-harmonic functions? If it is at most linear growth, then it's actually affine?
For PM, I didn't consider this question, but for PM, but this is a good question. I didn't consider this. For PM function, I think this is true because you have regularity theory.
Mhm.
I mean, yeah, here you give an answer. If we have some regularity theorem, this yeah, for PM that's true. If you have regularity, say C1 alpha regularity, then this must be true. Yes, because using this several regularity, this is just 4 or 5 lines proof from the regularity. And then regardless of this conjecture, there's some progress. The first progress is given by Crandall Evans in 2000. That shows if U is an infinite Hamming function in the whole Rn, and if this pointwise Lipschitz constant is reached at some point, this is important, then this must be some linear function plus constant. And then later, they show some sequential differentiability along given any point, given any subsequence. They can find a subsequence such that blow up along this subsequence, we will get some linear function. But this plane, this plane depends on the sequence itself. If this sequence independent of this, if this plane independent of this sequence, then you will get everywhere differentiability. And then this is, and at infinity, there's a similar result. I don't want to say it. And then Evans smart shows this U is, if U is infinitely harmonic, then you must be differential everywhere. The point is that they show that this you blow up in different sequence, you get the same plane. And we can show some result. When you blow down, you will also get some, you will converge to some plane. This is done by Yuan Zhou and also me, but I don't go to details. And Savin in dimension 2, Savin even show some more result. He showed that the infinite-harmonic functions in plane, it must be C1 regular, C1. And then later he, with Evans, shows the planar infinite-harmonic functions are C1 alpha. And Savin's proof is difficult. And I think the point that he used a planar topology to show the following things. If this is planar infinite-harmonic functions are close to x1 in some ball, you can always assume this. And also the Lipschitz constant is small in some smaller ball. Then they find a curve, contact the boundary of the small balls and to this unit ball. And along this curve, the pointwise Lipschitz constant will increase, but it increases very slowly. This is the point. They use the planar topology. So in hard dimension, one cannot use this sense. But it's also not known. In hard dimension, semi-regularity is not known. And also uses this regularity, he gets this newer property. Use C1 regularity and the compactness argument. And if you use C1 alpha, they can even get something better. And what we do recently is that we use a larger approach to show if you use a planar infinity-harmonic functions, we show this gradient du with power alpha in W12, and with this kind of second order regularity, and with this kind of control. And we also show the determinant, the Hessian with the Jacobian is a Radon measure with this lower bound. And for any alpha larger than 0, we show the du with power alpha times du. This is almost 0 everywhere. Previously is low in viscosity sense, but we show it is almost everywhere. And we proved this in 2019 with Koch and Yizhang. And because here our function is in Lipschitz or even better in C1. But then how to define this kind of determinant of Hessian is a problem. But we already know, you always can define this in this distributional sense. In fact, we can define this, the determinant of this kind of d square u, the Hessian. The formula times psi, the integral is given by 1/2, then integral over omega with d square psi times dv, then dv, and then minus this integral over omega with du square Laplace psi. Here we get second order, here we only have one order, so we are done. And how to get this formula? The formula comes from this relation. This determinant of d square v is given by this d square v with its length power minus Laplacian u. Then you get write this as a divergence form. And for inside guy, you can further write it as they have a larger divergence structure. So this means you have two-layer divergence structure. Then you can define this. Moreover, we found that this is given by this. This d square v, dv with power with length with power 2 minus Laplacian v, infinity Laplacian v equal to this. This is just this guy. Once you write once you get this relation, this is very important because this kind of structure of infinity Laplacian. Once you this guy we know it has a second order divergence structure. And then this is some good sense. And if this is zero, infinity operation V is zero, then this will immediately gives this result once you observe this identity. And also in the literature, there's Yuan Zhou and Manfredi, they try to understand this planar infinity-harmonic functions using complex approach. But however, I don't say not very nice result available. So it is quite open to understand this planar infinity-harmonic functions by this complex approach. For example, to get the sharp regularity, 7 1/3, or W2Q regularity. I mean, what I mean is I try to extend this Ivanich and Manfredi's approach for Laplacian to infinity Laplacian. Is there some good way to extend it? That tried something, but didn't get very good result. But still, we wish because once you want to get some sharp sense, the complex approach always give you some convenience, or gives you some new insight. So that's somehow I try to understand, but till I didn't have I didn't have any idea for this. But with this kind of second order regularity, we'll see a very easy proof for Simon's neural theorem. This is also the meaning to study the second order regularity. I can introduce it in very quickly. But we don't use C17 alpha. We just use second order regularity because we can first show. Indeed, we can show under this condition once the oscillation at enlargeable as the oscillation goes to zero, then we can show this function u must be linear function plus some constant. To prove this, we only need to prove this length of the du is a constant. And then we will get the length of du is derivative is zero, and then use our result. We can show that Jacobian is zero. Use our result because this is zero. Use our this result. Use this result. We'll say this is zero. Once you get this is zero, you can easily get u is a constant. And we use the calculus of this. We find some formula. Just from this calculation, we'll get some formula for this. And then we'll show this du is controlled by this. This pointwisely, the derivative is controlled by this kind of oscillation. And then we will show that this will go to infinity, will go to zero. You will go to blow down to some plane. You will blow down to some plane. And then use this relation. We'll get this is controlled by this. This is controlled because this is controlled by this, and this guy is controlled by this, so this is controlled by this. And this is what blow down to some zero, so directly calculation shows. We also show this. So we only need to control this by this. Control this by this. And a directly calculation shows this guy will controlled by this plus this. And once we have this, we're done. So this means this is controlled by this controlled by this plus this, and this already know it goes to zero. Then we get rid of that.
Sorry, can you go back to the previous slide just to for the main for this statement? So what are the assumptions here? So what does that essentially say?
The assumption, our assumption.
Yeah, what does that roughly say? So if the function has linear growth, is it satisfied? No, not necessarily.
If this is, I mean, if a function is linear growth, then it must be bounded pieces.
Mm-hmm. I see.
If it is bounded pieces, then uh, this is goes to, yeah.
Okay, yeah, thanks.
So that means our idea is just control this using this. This is the point. Then we go back to our limited problem for p-harmonic functions. We already know in a domain with limited boundary, this p-harmonic function UP will converge to the infinity harmonic functions in C1, C0 alpha and W1Q. And based on this result, linguists and Lindgren, they observe that this UP will goes to U infinity in W1Q sense for any Q. He improved from the weak to this norm. So they proved that this, but they just use our approach, use this kind of approach here. And so this, but interesting question is that, is this converges in C1? But that's quite open. Nobody knows, even in dimension 2. So this is even hard question than this several regularity of infinity harmonic functions. Because in the plan, Savin already shows that infinity harmonic function is C1. But if this converges to this in C1 sense, it's not known. But what we can do? We try to understand a kind of second order convergence, the possible limit of this guy. This nonlinear gradient and its Jacobi. Because this guy for p-harmonic functions, it has some geometry meaning. It is this guy is quasiregular. This V beta is always quasiregular. But the quasiregular, the coefficient will go to infinity. So we cannot expect more sense from the quasiregular property. But we wish this for this nonlinear gradient of DUP and take a derivative with Jacobi, it will goes to the derivative of nonlinear gradient of U infinity with Jacobi. In some sense, we wish that. And in the case of beta equal to 0, this is you can define this kind of Jacobi of the Hessian in distributional sense. But in the case beta not 0, a distributional definition for this is unavailable. Because once you define this, you need, in this case, U in W12 is enough. But in this, because you have linear structure, but you want to define for this, you need this guy in L1, at least in W, this V beta in W12. Because this is nonlinear, then you try to use this kind of divergence structure to define it, it's not easy. So a distributional definition for this is unavailable, at least as we know. And then recently we found a correct definition in the distributional sense for this guy. And for any in any domain omega, and for any beta larger than -1 and V in W12, and then with the additional condition, beta times dV with beta plus 1 in W12. I mean, if beta just 1, if beta just 0, then we don't need this condition. This goes back to the distributional Jacobi of Hessian. But if beta not 0, we need this condition. And then under this, we define this kind of nonlinear Jacobi, the gradient of nonlinear gradient, the Jacobi by this formula. This is given by this term. This term is similar to the case in beta equal to 1 equal to 0. Also, this term also similar to the case beta equal to 0, but we get a new term here. If beta equal to 0, this term disappear, but the beta not 0, we must have this term. And for this term, our condition, this our additional condition beta du is power beta plus 1 in W12 used here. Used here. Used here. We can compare this formula as the Hessian. As this. You can compare with this. In this definition, this corresponds to the case beta equal to 0 is given by this. So this term and this term corresponds to the case of beta equal to 0. But this term is new when beta is not 0. So that's we found this definition. And since in our previous paper already showed us this du infinity with beta plus 1 in W12, and this is derivative times du infinity is 0 almost everywhere. So for planar infinity-harmonic functions, the derivative of this nonlinear gradient and take this determinant is in the distributional sense is given by this. Because we already showed that this is 0 for planar infinity-harmonic functions. This is already 0 in this theorem. Here we already showed this is 0 for planar infinity-harmonic functions. Then the other sense is much similar to the case beta equal to 0. I mean, we realize we can define for this nonlinear Jacobi for the infinity-harmonic functions, maybe 2020 or something like this. But we found this definition in 2000. It's been 2 years to find this definition. But then with this definition, we can show for beta larger than -1, this is nonlinear Jacobi. The derivative of the derivative of a nonlinear gradient is non-negative Radon measure with this kind of lower bound and also some upper bound. And this is lower bound, upper bound. Yeah. And also for this p-harmonic function, we have the same similar upper bound. And this also coefficient is uniform in P. I mean, this is for infinity-harmonic functions. This is for p-harmonic functions. Now, for p-harmonic functions, this coefficient depends on P. But when P bigger than 2, we'll see all these constants are uniformly in P. So this means once we take P go to infinity, we'll get something. And then that's what we get. This determinant will converge to the determinant of the gradient of the nonlinear gradient of p-harmonic functions will go to the determinant of the gradient of the nonlinear gradient of U infinity in measure sense. Yeah, this what we got recently. And this is done with Hongjiedong and Peng Fan 的一章. I mean, the proof is not difficult. Once you have the definition for this guy, the proof is, I should say, it's really not difficult. But the point is, find the proof, find the definition for this guy. And then it's also the problem to prove this is reasonable. This definition is reasonable. It is reasonable. To find it and show it is reasonable. What we need to show it is reasonable. If we already know that's nonlinear gradient in W12, say for p-harmonic functions, this is already correct. Then you have a pointwise defined Jacobi determinant. This in L1. This defined pointwise. And then you must show, and then along our definition, we have a distributional definition. We must show this pointwise definition and this definition are the same. This point. We give a new definition, and why if it is coincide with the old definition, that's the point. This is our lemma. If V in W11 and dV beta dV in W12, we need to get this formula. But to prove this, it's not easy. Usually, idea is to try to approximating V by some smooth function, and the smooth function is always got by the convolution, by this standard modification, smooth modification. But once we use this, we don't know how to prove this. We tried very hard, but found it really difficult to control this term because there's kind of nonlinear structure. We have no way to control this. And then we found that if we solve some 2 plus beta equation, because we have a nonlinear structure here, this kind of comes from this beta plus 2 harmonic function. If we solve this equation, then we can use some result by Chunk and Mazia, the second order regularity. This will help us to get with all the convergence we desired. And then with this kind of, in particular, this kind of convergence of this guy and this guy. Once we have this, then we can show this definition is reasonable. Thanks. I think I stop here.
Okay, yeah, thank you.
Thank you.
I'll thank the speaker.
Yeah.
And let me start the discussion. Comments or questions?
Okay, please.
Yeah, can I ask a quick question? Can you go back to the definition of this? I think you call it V beta, right?
Yeah. V beta. Okay.
Can you go back to the definition of this? Yeah. Okay, I see. Yeah. So this is some other basis of this kind of complex variable approach.
Yeah, this is a complex gradient, and then times with the length, the kind of nonlinear complex gradient, I call it. Yeah.
And I mean, this beta here is in some sense arbitrary, and you choose it in some kind of an optimal way, right?
Yeah, this optimal range is beta minus beta bigger minus 1.
Yes. Okay. All right. So are there other comments or questions? Well, maybe can you say something about future directions? I mean, where do you want to go with all this? I mean, this regularity that you mentioned for infinity.
Yeah.
Is this the main question in the field, or?
Yes, that's this question. Yeah.
Oh, this.
I mean, this conjecture. Yeah. I mean, one direction is work with the sharp one in the plane. Work with say 1/3 or W2Q regularity. But this kind of PD approach, I didn't see any hope till now. A possible way is using complex approach, but complex approach, we cannot go to some thing as Manfredi and Yuan Zhou does for the p-harmonic functions. So how to use complex analysis here is a problem because in dimension 2 complex analysis always provides a powerful tool. Yeah. That's one direction. Another direction is working same regularity in higher dimension. In dimension 2, this is done by Savin, but he used planar topology. But in higher dimension, this is somehow, I mean, you don't have any approach. And recently we can prove something. We can for in this convex ring. I mean, inner domain is convex, outside domain is convex, and in this kind of ring, we can show this infinity potential are C1, and this P potential converge to infinity potential in C1 sense. In our recent paper, we just submitted some months ago. But for this general infinity-harmonic functions or the 7 convergence of p-harmonic functions is not known. I think this should be it deserve to understand. In particular in the dimension 2, can we use some complex approach to understand this? This is
Very
I think it's interesting.